Hello everyone. In this lecture, we are going to talk about the timers and the counters. Timers and the counter is one of the important topics in embedded systems or microcontrollers or microprocessor architectures, because we can use timers to create delays, we can use counters to count an event, and so on. So in this section, we are going to see the generic counters and the timers. How are we doing timing in AVR? So the AVR specific registers that we are using, the flags and so on. And how are we doing accurate calculation of the time so that we can set the registers? How can we generate a waveform from the timers? Generating large time delay. So we have seen to create a type of delays, but if you want to create a large type of delays, we can use timers as well. Timer reset on compare. This is a CTC mode, which is a special function in the timers which performs a compare rather than the overflow. We are going to see this in detail as well, and the different timers in AVR. So different family of the AVR family, we have a different types of timers in them. So we are going to see the Atmega 128 specific ones. And how are we doing with the counting events? So let's give a start and start with a counter register. So generally, if you want to perform any counting or timing events, we have a register for the counting, which is known as counter register. And that counter register is actually, we have got some kind of a clock input, the load, and we have got some C out and some other stuff. So as you can see from the example over here, we can actually put a sensor over here. So whenever we detect a pupil, that will tick on the clock, and actually the counter will start to increment, or it can be a decrement when we set to a value. So it's either getting in or getting out from the room. So the comparator value sets to 4, and so the output is 1 when sensor triggers, and initially it's at reset, so the counter the 4 times. So when the 4 times is reached, it just sends an out, and we have full, let's say, the room or the limit has reached and so on. Or it can have an alternative design where again the sensor is connected. We have got a 8-bit input coming in. So output is 1 when sensor triggers the counter, which is loaded with FC. So 4 times, then the overflow happens. So we are going to see this in details. Right, so if we get into more details of this, many applications needs a count on an event, or maybe to generate time delays. So that's why we have got these counter registers in the microcontrollers. And when we want to count an event, we connect the external event source to the clock pin and of the counter. So I'm just gonna go for the next slide over here. So we have got a multiplexer over here, an external source is connected. Then when an event occurs over there externally, the content of the counter is incremented. So when it reaches to a limit or it reaches to the end and it overflows, it sets the flag. And it's actually the content of the counter represents how many times an event has occurred over there. And if you want to generate a time delay, not counting an external event, we connect the oscillator side. So to the clock or the counter, and when the oscillator ticks, the content of the counter is incremented. So in the end, the content of the counter register represents how many ticks have occurred from time we have cleared the counter. So 2 ways of using this, and this is actually showing us the difference between the counters and the timers. And as we already know the speed of the oscillator in the microcontroller, the clock or the frequency of the microcontroller, we can easily calculate a tick period, And from the content of the counter register, we also know how much time has elapsed. So if we want to give an example, there are two methods that we can use over here. Method one is we can generate a time delay by clearing the counter at the start time and wait until the counter reaches to a certain level or a number. So let's say, for example, let's say we have got a clock frequency which is 1 megahertz, and let's say the contents of the register is incrementing, in this case 1 per microsecond. So the period is 1 over 1 megahertz, which will give us 1 microsecond. So if we want to have a time delay of 100 microseconds, that means we should clear the counter and wait until it becomes equal, the register becomes 100. So as this is 1 microseconds, we need to have the register to become 100. So that 100 times 1 microsecond will give us 100 microsecond delay. The second method, in the microcontroller, there is a flag for each counter. And this flag is set when the counter overflows. And this is cleared by the software by itself. So to generate a time delay, we load the counter register and wait until the counter overflows. So let's say we start, as an example, from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, let's say 10 as an example. Then after 10, let's say it's gonna overflow. So over here we set a flag to 1, and then this goes back and starts again. So again, as an example, we have got a frequency of 1 megahertz, and we have got an 8-bit counter register over there. So if we want to have a time delay of 3 microseconds, we can load the counter register with, as this is 8 bits, we can load it with FD. And we can wait until the flag is set after 3 ticks. So how is that going to happen? After the first tick, this is going to be FE. So let's say first tick. After the second tick, this is going to be FF. And after the third tick, it overflows. So maybe somewhere here I can just do that. So when the third tick occurs, the contents becomes 0, 0. So it overflows and starts again and counts up to FF and goes back. So whenever, wherever, let's say in this 3 microseconds we want a delay, we start from FD and count to FF, then it overflows and so on. If you want to have more over there, we just need to set it maybe on a previous or any type of value that we want. So we are going to do an example related to this later in this chapter. Now, AVR has got 1 to 6 timers. It depends on the family that we are using. In Atmega 128, we have got 4 flexible timers. And these two, one of the important ones are the timer 0 and timer 2, which is an 8-bit timer. But before we go into the details of that, we have some important registers and the flags that we need to take care. So for example, TCCR is the timer control register. So timer control register is used for, like the other control registers in AVR, is used for setting the modes of the operation. We are going to see the details in the coming slides. And we also have TCNT, which holds the value that we want to have for the delay or for the counting events. And the TOW, which is timer overflow, as we already described previously, when it starts from 0, 0 to go to FF, when it reaches to FF and goes back to 0, overflow flag sets. And OCRN, it's another register, which is represented over here. When you load the content of the OCRN to a set of values, a specific value, and your TCNT is incrementing to that value or decrementing to that value, when it reaches to OCRN value, this is going to be equal to, so there's a comparator over here, and output compare flag will be set. So based on the comparison, this will be set. So we have two modes of operation. Either we specify the value that we want to reach, or we can wait for the overflow, but we have to set it where to start this counting event. And as we already said, we have got 4 types of timers and the counters, 0 and 2 for 8-bit counters, and 1 and 3 for 16-bit counters. And all timer registers are byte addressable I/O registers. So that means we can use in and out instructions to perform or set these registers. So we can say that the difference between the timers and the counters, every timer needs a clock pulse to tick. So the clock source can be internal or external, which we already seen it over here. Therefore, if we use an internal clock source, the frequency of the crystal oscillator is fed into the timer. So we can say that the time delay generation is occurring over there. This is called a timer. Or by choosing an external clock option or the external source, we are feeding the pulses through the AVR pins, and this is called the counter. So next we are going to see the structure of these 8-bit counter 0 or 2 structure or the architecture itself. So there are a few things that we need to take care over here. So TCCR is the control register over there. We have got some kind of control logic which is used to set the TCNT, and OCRN, output compare module, is still there, so that part is actually over there. We can use it for waveform generation. And we have got a prescaler, which we are going to talk about in a minute. And also we have got the oscillators and the clock, internal or external clocks, that we are going to use over there. The TCNT register is a counter. So it's a counter register, and when we reset it, it's 0. It counts up with each pulse, as we already seen it. And the contents of the timers and the counters can be accessed using this TCNT register. And we can load or we can read the value of this register. So in that register, to reach that register, as we already seen it, we have got a control logic. And this control logic has a timer overflow flag. So we can set this by using interrupts, or we can just monitor it by polling. And we have got top and bottom maximum and minimum values of the TCNT, in this case 0. timer zeros, and the direction and the count incrementing or decrementing up and down, and the clear is just resetting the TCNT. So another important thing over here is the prescaler. Do you know what prescaler is doing? Prescaler is actually like a clock divider, which we generally use to reduce the high frequency electrical signals to the lower frequency by integer division over there. And the purpose of this having over here, we are actually allowing the timer to be clocked at the rate a user desires. So we can choose how fast we want to use this timer or how slow we want to use it based on the application. And the prescaler can be coming from the internal clock or external pins, which is TOSS-C1 and TOS-C2. So next thing that we need to consider is the TCNT2, which is timer counter 2 in this case. The only difference is that we need to notice over here, we have got this prescaler input coming in with the multiplexer, but we also have the edge detector over there, which is, there's another pin which is connected. So timer 2 is also an 8-bit timer, which is exactly working in a similar manner with the timer 0, but there are some differences between them. So, for example, timer 2 can be used as a real-time counter. So we need to connect a crystal with some certain frequency to TOSS-C1 and TOSS-C2 pins. And we have to set some other pins over there. And you can find more details about this. Or in timer 0, when we have got CS02 and CS00, bits, which we are going to see in a minute in the control register. When we have certain values over there, timer 0 counts for the external events. But timer 2, the multiplexer selects between the different scales of the clock. That's why we have got this multiplexer over here with these scales. And it actually detects the edges as well, if it's going to be a rising edge or the falling edge and so on. And we are going to see a little bit more details on the later. So let's see the most important register in timers, which is a timer counter 0 control register. Now over here we have got 8 bits in these cases, and we are going to describe those as well. So each timer has got this control register, and we can use this to set the mode of the timer. And the first bit, which is bit 7 in this case, which is D7, let's say, over here, is the FOC0 bit. It's the force compare match. So this is only the write-only bit, which can be used to generate a wave or a waveform. So by writing 1 to it, it causes wave generator to act as a if compare match had occurred over there. We are not going to consider that at the moment. We are going to focus on the other control bits over here. So VGM00 and VGM01. These are VGM00 and VGM01. These are our timer modes select bits. So for example, D6 and D3, they can be 00, 01, 10, or 11. And when it is 00, if we set them to 00, it's a normal mode. If we set them to 01, it's a CTC mode. Then PWM. And of course we have got a fast. So fast PWM. So in this chapter we are going to consider those two, and for the later we are going to see the PWM and fast PWM versions of it. And Two other bits over here, which is COM01 and COM00. It's related with the compare out mode, which we are going to see that in a minute as well. This is also used for waveform generation. Now, the last three bits, which is CS02 to CS01 and CS00, it's actually the clock selector. So we can see the table from here that we can use either without the prescaling or with a prescaling. So we can do the clock division or not. So if you don't use a prescaling over here, this is a typical normal mode operation. Then it starts to count with the ordinary clock. Without the prescaling, the TCNT increments up to the maximum point, which is, if it's a 8-bit counter, that means FF. So when it reaches to FF, timer overflow flag is set, and then it can be cleared by the software. This goes back to the bottom to 00 and starts counting up again and again. Or if we are using a prescaler, we can slow down the clock, let's say in this case by 8. And as you can see, the clock pulses over there. So the new values are coming in when the clock pulses are in there. And again, when we reach to the maximum, timer overflow will indicate it reached to the maximum. So we have to go back and start again. So this is a one way of operating this. The timer counter control 2 register, which we already set. These clock selectors are a little bit different. So we have got different prescalings over there. And also we have got external clocks. So TN, which is T2 pin over here, it can be set for the falling edge or on the rising edge when you want a counting external falling or rising edges. So this is another functionality of timer 2 control register. And another important thing in the timer counters is the output compare. So the OCRN, output compare register for 0 or 2, the content of the register is compared with the content of the TCNT. So that's what is happening over here, which we have seen it previously as well. So 8-bit values are compared. When they are equal, the output compare flag is set. So when this flag is set, you can use this flag to generate a waveform or to interrupt to an external event to something else. This can be done with OCFN when it reaches to certain value. So like we have said before, the timers are located in I/O memory, and we can read or write the timer register using in and out instructions. So when we do these examples, with the coding examples, you will see what I mean. So let's move on to the next slide. So the timer 0 or the counter control, So VGMN0 and VGMN1, which are the modes that we already mentioned. So CTC and the normal modes that we are considering in this chapter, and the PWM and fast PWM, we are going to see those later on. Now, what is important over here is when we are in a, let's say, normal mode or any other modes, as you can see, OCRN value is reaching to a certain point, okay? But the most important part over here is the timer overflow flag, because we don't have any CTC mode enabled, which is done over here. So it doesn't need to reach to a certain value. Even if it reaches there, OCFN flag is set if you want to monitor it. Otherwise, the timer overflow flag will be set when it reaches the maximum and then overflows and starts again. But in CTC mode, we are actually considering the OCRN, the top value, and when it reaches there, OCFN is set. So they are pretty similar to each other. The one of them is checking for the OCRN value, the other one is not checking the OCRN value and it's just checking for the overflow. So I'm going to explain this in details in the coming slides. So let's say we have got started with 0, 1, 2, 3 and goes up to FE and FF. Okay, so we count up and so on. When we count up, what is happening with the TCNT is so the maximum limit that we can have is 0 hex FF over there. This is our TCNT N register. So we start from 0, we go up to FF, and when we reach to FF, it goes back to down. So over here, TOV is occurring. So we can say that TOV, which is a timer overflow for counter N, is going to be 1. Then it starts again, it goes up. When it reaches to FF, it goes down again, another TOV occurs, and then up again and down again and so on. So this is going over a time, and we can see that how this is working in a normal mode. So this is known as normal mode. It goes up to FF. When it reaches to FF, it overflows, it rolls down to 0 and starts again. This is the normal mode of operation. If we want to do this in CTC mode, what we are having is we have got a certain value for CTC. So OCRN has got a value XX, let's say, and I start to count 0, 1, 2, 3, and so I reach XX, and then there is FF somewhere. Okay, so I go up out to there. When I reach to XX, which is set in the OCRN, this will roll down back, so it's not gonna go up to FF. So the timing of this can be shown again with TCNT. This is output or clear timer on compare match, let's say. So start with 0, we have got XX somewhere there, and we have got FF somewhere there. So FF is never going to be reached as XX is somewhere in there. So when we reach there, for XX, this will go down. And in this case, OCFN will be set. So output compare flag will be set. It's going to be 1, and TOV N is going to be 0 because we will never reach to FF. And again, goes back to 0 and counts up to XX, goes back to 0, counts up to XX, and so on. So it's always OCFN is raised over here. And this is how it's generally working. And one other thing that we need to consider is the compare match output modes. So when you want to do CTC mode, which we already explained on the board, You can have a normal operation, so OCN is disconnected. You can have a toggle OCN on compare match. So if you want to generate a waveform, you can use this. You can set it to 0, you can set it to 1, or you can, if it is 0, it will be switched to 0, 1, or so on. So you can toggle it as well. And this is also valid in timers. Now, the next thing that we need to consider is the timer interrupt flag. So the timer interrupt flags are actually set in the timer interrupt flag register. And these are related with the different timers that we have got in AVR. So we have got timer 0 flags, timer 2 flags, and we have got timer 1 and so on. So TOV0 is the timer overflow flag. So when it is 0, it did not overflow. When it is 1, it has overflowed, so it will set to 1. OCF is the timer 0 output compare flag. So it's 0, match did not occur, and 1 for match occurred. And TOV1 timer overflow flag for timer 1. And OCF1B and OCF1A is the timer 1 output compare B and A match flags. And ICF is the input capture flag, which is not related in this case. And TOV2 and OCF2 is similar to timer overflow 0 and timer OCF0. So you can find the details in the datasheet as well, but that's how it's generally working. And so the timer 0 and timer 1, or the counter 0, counter 1, they look exactly the same as we already said. They have a different flags or the register names, and the operations are, as we already said, with the CS22 and CS0 and so on. The only difference is this is set as you can see with the prescaling, without prescaling, and goes to 124. This is also has 8, 64, 256, 124, and also external clock. So the falling or the rising edge of the clock can also be configured in this mode. So there's one thing that we need to take care. When we talk about the timer overflow flag, which is TOV in this case, we need to be careful over here, because there's a strange thing, like in order to clear the timer overflow, we need to write 1 to it. So this is a bit strange, because writing a logic 1 to it actually requires only a single out instruction, and it is clear that only this single interrupt request will be cleared. So there is no need for read, modify, write cycle, and since all bits are in the control registers are, interrupts will not alter them. So we can use this flag, and when you want to clear it, we have to set it to 1. And like other flags, the other flags in AVR also has to be cleared using 1, and we can set this using the out instruction, and we can just clear it. So the next thing that we need to consider is a simple example. It says write a program that waits 14 machine cycles in normal mode, no compare match, and toggle PB5 after this delay continuously. Okay, so we need to use the normal mode, and that means we can detect the overflow after 14 machine cycles, and also it has to toggle PB5. Now, so to generate this type of delays in timer 0, first we have to set, as you can see, the PB5 to be an output. So we have to set DDRB5 and initialize port B and clear everything. Then in a loop we start to load the timer the counter. So when it says, so let's find the mathematics first. When it says 14 machine cycles, so 14 machine cycles is actually, hang on, is what? That means 14 in hex is 0 hex 0e, right? That's 14. Now, if you want to have 14 machine cycles, that means the maximum that we have is 0 hex ff, right? So from ff we have to subtract that OE to find out how many times we need to count. So when we subtract that, what we are going to get is F1. Now, this F1 is actually showing us the 14 difference, but we also need to add an extra clock for FF2 00 roll. So that overflow or rolling needs another extra 1 clock. So that means that is going to be F2. So this is the value that we need to set for TCNT0 register, which is saying over here load timer counter 0 with 0 hex F2, and configure timer counter to be in normal mode using clock IO. So it's going to be in normal mode, loop until timer overflows, and stop the timer. So how are we going to, so we know that TCNT 0 will be F2. How about TCCR? So F of C, it's going to be 0 because we are not going to use that. VGM00 and VGM01. So VGM00 and VGM01, we want it to work in the normal mode. That means, so D7 is 0, D6 is 0, then we have D5, D4, D3, D2, D1, and D0. So D6 and D3 is going to be set 0 for the normal mode of operation. We don't want any timer on compare much over there. Then compare output mode, we don't want that part as well because we are not comparing anything over there. So that has to be set to 0, 0. Then we have got D2, D1, and D0. So D2, D1, and D0, depending on the timing that we want to use. So it's asking us to use a no compare match using clock IO. So that means we don't need any prescaling or anything like that. That means we have to set it to 0, 0, 1 in this case. So when we want to set it to 0, 0, 1, that means this is going to be 0, 1 as the register value that we need to load to TCCR0. And TIFR, as we are looking for timer overflow flag, we need to check TOV 0. If it is 1, so we need to check TOV 0 if 1 or not. So it's giving us all the structure of it. and when it reaches to, or when it overflows, we have to stop the timer, so we have to reset the TCCR0, we have to clear the timer overflow flag, and as it's asking the question, we have to toggle PB5 and so on. So now let's write the code for it and let's see how it is going to work. So I'm going to change my screen. So what do we need as a start? We need to set the port B to be an output port. So let's say, let's write in capital, LDI R16 to be, so we can just set the port B pin 5. So to set the port B pin 5, we can just write 0 hex 20 over there. Hang on. If we do that, yeah, that's the one that we need to toggle, so let's skip that one over there. We can set the SPI DDRB 5 over there, so we can say that this is PB5 as an output. Then we can clear the port B, so R17 to be 0, and we can say out port B to be R17. Now the next thing that we need to do, we have to load the timer counter value, so LDI R20 0 hex F2, which we already calculated, and that's going out to TCNT0 register, and we have got R20 over there. So we can say load timer 0. Then we need to set the TCCR register LDI R20, and we set that it's going to be hex 1, so 0 hex 01 over there, and that's going to be out TCCR 0 register, and that's going to be R20. So we can say that this is timer 0, normal mode, and internal clock. Okay, and then, so now we can check for the interrupt flag. What do we need to check? We need to check if the timer 0 overflow flag is set or not. So that's actually like a checking and getting the value of that register, and if it is set or not, we have to compare it. So I can say that in R20 timer interrupt flag, timer interrupt register. So let's say read TIFR over there. Then what we can do, we can use SPRS instruction R20 0. So what it's saying actually, skip if bit 0 is set or not, which is the TOV flag. So we can say that if TOV is set, skip next instruction. And what we are expecting over here, we have to wait. So we have to do a polling over there, and we have to wait. So to wait over there, we need to use some kind of a jump. So let's say R jump again. And now where are we going? We are going to keep checking the interrupt flag register. So we need to have again somewhere here. So let me just tap this. So they're all in a similar indentation. And that means we have to jump it over there. So that means if it's not set, we have to keep checking when it is set. So if it is set, what we'll do, we are going to do LDI R20 hex 00. So we have to stop the timer. So to stop it, we have to set it to 0. That means that is going to be out TCCR0 R20, and that will stop the timer 0. And we also need to clear the flag. So TIFR, oops, sorry, LDI R20, it's going to be the first bit needs to be set. So we can say TOV0 to be 1. This is what is actually clearing it when we are setting it to 1, and that will be out TIFR R20. So that will clear TOV0 flag. And I'm just gonna add a comment for that one as well. So R20, it's actually equals to 0 hex 01. So we cleared TOV flag, and then we just need to toggle port B. The last thing we can do, XOR over there, R17, which is 0, XOR R16, which is already set. So then this will toggle bit 5 of R17, and we just need to send this out to port B. So then what is happening is we have to repeat this continuously. So that means we need another R jump over here. And where do we need to jump? We have to reload the timer and start again. So I'll say begin over there, and that begin has to go back to where we load the timer, which is over here, and we can write begin over there. So whenever the begin is called, we initialize the timer, TCN, TN, TCR registers, and then we loop through to check the interrupt flag, if it's set or not, the overflow flag. So when it's not set, we just wait over here, loop over here, and when it is set, we clear the timer, we clear the flag, and we toggle the outputs. So that's how it generally works as a code-wise. when you want to wait for 14 machine cycles. I hope it's clear and understandable, and we can proceed to the next stages. So when we consider these things, we need to ask a couple of questions. We are calculating the delays, but are we calculating efficient enough? That's the first question. And the second question that we need to ask, how are we going to calculate the delay generated by the timer? So we need to calculate how much a machine clock lasts. We need to calculate how many machine clocks it waits. And then we can calculate the delay, which is related in the both two that I already mentioned. So let's go back to the slides. And to our board again. So now the question, as I already mentioned, how to calculate the delay generated by the timer. So calculate how much machine clock lasts, so T is equals 1 over F, and calculate how many machine clocks it waits, and then the delay. So if we start with the T is what? T is 1 over F. So let's say we have got 10 megahertz clock that we generally use. This is going to be 1 over 10 megahertz, which is equals 0.1 microsecond. So we got our period over there, and we need to calculate the number of machine cycles. So we already said that it's using 14 machine cycles that we need. So we can say that 14, which is OE, 0E, that we need over there. And to calculate the delay, we can just say delay is the period, which is 0.1 microseconds by 14 machine cycles, which is going to be 1.4 microseconds. So this is the one solution, but it's not really the accurate way of doing this. Now, let's consider the second solution. So the second solution, so we know that this delay is 1.4 microseconds. So how much does it take for instruction execution? We need to consider that as well. So to consider the instruction execution, we have all the instructions over here, 1 cycles or the 2 cycles that it needs. So in total we have got the delay as, for the instruction execution, delay, which is 17 machine cycles. When you multiply with 0.1 microseconds, that's going to be 1.7 microseconds. That's another delay. So in total we have got 1.4 plus 1.7, 3.1 microseconds. So this is actually the period, one cycle that we have. So it's not a cycle, it's how do you call it, it's the one of the levels that we have. So to find the wave period, so that means this is like, if I draw it, so 3.1, it's actually this period, this time over here, or maybe this time over here. So for one cycle, we actually need two of these to say the period of the wave. And period of the wave, it's going to be 2 times 3.1, which is 6.2 microseconds in these cases. Now, to find the wave frequency, this is so simple. We just need to divide that 1 over 6.2, microseconds, which will give us 161.29 kilohertz. So this is the wave frequency that is going to be generated. Now, we'll do more examples related to these to understand it better, but the general idea is showing over here. To generate that type of time delays, we need to have a wave frequency of 161.29 kilohertz and so on. So the steps are over here, calculating the value to be loaded to the timer. So calculate the period of the clock source, 8 megahertz, 10 megahertz. Based on that, we can find the period by 1 over the frequency. Then divide the desired time delay by a period of the clock and perform 256, which is FF minus N, where N is the decimal value that we got in the previous step, and set the TCNT based on that. And we can also put this into a formula. So if we are considering in hex, that means we can say that FF minus the hex value plus 1 for the overflow times the period. And this is in hex, as we already said. If you want to do this in decimal, that's going to be 256 minus the decimal number that we are having, that we already get it from the desired time delay, multiplied by the period. So these are the two important things that we need to remember when we want to do any type of calculations. So now let's see an example related to this. It says, assuming the clock frequency 10 megahertz, write a program to generate a square wave with a period of 10 microseconds on pin port B3. Now, before we do the program itself, let's do the calculations first. So we have got 10 megahertz clock. So that means that's going to give us 1 over 10, which is 0.1 microseconds of the period. So for 10 microseconds for the square wave, that means the period of the wave is 10 microseconds. So this is actually telling us that that wave has got 5 microseconds low and 5 microsecond high time. So that means we can say that 5 microsecond divided by the clock period we are going to get 50 clocks. So that's another thing that we need to have. So that 50 clocks, it needs to be subtracted from 256. And that is giving us 206, which is going to be, the value needs to be loaded to TCNT0. As we have got this, and we know that this is going to be work in a normal mode, as it's not specifying any output compare and so on. That means our TCCR0 has to be loaded with 0 hex 01. So we have all these necessary information, so we can just write the code for it. So let's write down the code for it. Was it this one? No, it's not this one. I remember I created something so that we can start doing it, but I think it's not there. Anyway, so we can do with the new page. Let's set it to assembly. So we have got 10 megahertz clock, and we need to generate square wave with a period of 10 microsecond again, and we need to generate this in port B pin 3. So let's start with LDI again. I'm gonna start from identification so that we can, if we have any loops over there, we can easily cover that. LDI R16 0 hex 08, which is going to be the third pin of port B. Then SPI DDRB 3, so PB3 as an output. Then what we do, LDI R17 0, then out port B R17. So we just set what's gonna happen with the port B. Then we start loading the timer values. So LDI R20, the value is 206 as we already calculated, and that should be out on TCNT0 R20. Then we need to load the control register LDI R20 with hex 01, and then out TCCR0 with R20. So let's just write a comment as well. Load timer 0, then timer 0, normal mode, internal clock. Then we start with the in, and we have to check the TF timer interrupt flag register. So reading TIFR. So again SPRS R20 TOV0. So we can say that if TOV0 is set, skip next. And R jump again. So it has to go back and keep carry on checking. So that's going to be again. Then we carry on. So if the flag is set, we have to clear the timer. So LDI R20, it's going to be 0 hex 00, and that has to be loaded to out TCCR 0 with R20. So we stop the timer. Then we do another LDI, and we have to actually clear the overflow. So to do that, out TIFR R20, clear TOV0 flag. So we have done that. Then we have to do the port B toggling again with the XOR R17, R16. So it's pretty similar to what we have done before, only the TCNT value is changed over there. Toggle bit 3, and I think the port is changed, R17, and then out port B R17, and we have to go back and start again. So R jump begin, and that has to start from here. So we have to start over here. Sorry, wrong place. So that's our 10 microsecond period generator. We can also write this in C, but I want to concentrate on assembly. This is more important with the assemblies and so on. And that's also showing the same code. We can also do this using in CTC mode, which we am going to mention in a minute. So that's done. That's done. So I'm just going to open a new page to talk about CTC and the other related stuff. Now with the CTC, as you can see, this is the code for it, and I'm just gonna go back to my whiteboard. So the most of the things are similar over here. The only thing that we need to change is, which is highlighted with the blue, as it says the 50 clocks over there, which we already calculated in the previous. I'll just show you again. So we have found the 50 clocks over here, as you can see. So that 50 clocks, it's going to be our compare value for the OCRN, which is the output compare. And for 50 clocks, we need to set OCR 0 to be 49. So in CTC, 50 clocks means we have to count 50 clocks means we have to count from 0 to 49, isn't it? So we need to set OCR to be 49, as you can see over here in the timer stuff. And when we set that, we load the OCR with the timer 0 value, and then for the control register, the timer control register, we just need to set it to CTC mode. So we have to change the bits to be set it for CTC mode, and that's coming with the hex 9. You can check the register and set this up, and the rest is over here. Again, we are checking the interrupt flag, but rather than checking the TOV0, which is the timer overflow flag, we have to check when this is matching with the TCNT value. So OCF has to be checked. So when the OCF is 1, that means they are matching. The comparator says they are equal to each other. We have to skip this bit, and we have to again stop the timer, clear the flag, and set or toggle the port B pin 3. So the only thing that we are changing over here is this part, which is the OCR value, then the TCCR for CTC mode, and we have to check OCF flag. The rest is similar to what we have already covered. So I think these are pretty straightforward to understand. If you have any question, you can write it down and ask me during the question and answer session. There is one more example that I want to cover. So that is from the code is given to us. So it says find the delay generated by timer 0 in the following code. Do not include the overhead due to instructions. So we have got an 8 megahertz clock, and we need to find the delay related to it. So where do we need to look at when we want to find the delay? We need to look at the TCNT value, which is 3E in this case. And then we need to use the equation that we already defined for it, which is FF minus the hex value plus 1 multiplied by the period of the clock, so that we can get this in the period that for the wave, or we can do this with the decimal as well, and that value will give us the width of the pulse. So in this case, as this is 3E, I'm just gonna go back to my whiteboard. So 3E means FF minus 3E plus 1. So this was the equation that we need to remember. So that is coming to 0 hex C2, and 0 hex C2, you can find that is 194 in decimal, and 194 multiplied by 1 over 8 megahertz, which is going to be 194 multiplied by 0.125 microseconds, and this will give us 24.25 microseconds, and this is the width of the pulse that we have. Okay, and that's another example that we can consider. So the code is given, and we can easily calculate the timing based on the TCNT's values. So this one, so 10 megahertz clock and write a program to generate a square wave for 12.5 microseconds. This is actually similar to what we have done, which is this one, because we have done that for a 10 microseconds. It's exactly similar, so you just need to change 10 to 12 microseconds and you will get the same thing. So you can try that if you want. And on the slides there is another question related with this. So modify TCNT0 in example 2, which we have done it over here, okay, which we got 206, to get the largest time delay possible with no prescaler and find the delay in microsecond. In your calculation, do not include the overhead due to instructions. So what do we need to consider over here? To get the largest delay, again, we have got a what do you call the clock frequency as 10 megahertz. So F clock is equals 10 megahertz. Now the thing is that is asking is the largest delay possible with no prescaler. So the largest delay is actually, we can get it from 0, 0 to count up to FF. So that's the largest that we can get. So in order to find that, this is actually going to be 256 times. That means we can set TCNT 0 to be 0. Starting from 0, it will count up to 256. And the delay can be found, in this case, 256 multiplied by, this is giving us 0.1 microsecond period. So that is equals to, oops, I thought I opened this app. So TCNT 0 delay is 256 multiplied by 0.1 microseconds, which is going to give us 25.6 microsecond delay. Okay, so this is how we can use this and we can get the largest delay. If you want more delays, so that means that 0, that is changed, and we can just use the same code over there and we can perform the same operation, and that's the calculation for it. So if we want to generate a larger delays, we can use the loops that we have discussed before, loop inside of a loop like a nested loop, or we can use the prescalers, which we are going to see next, or the counters. So by using a prescaler or counter, we can bigger counters, we can generate larger delays, which we are going to see next. Okay, so with the prescalers, we can actually define what should be the clock division over there, so how slow we want the clock and so on. And generally these are as we have already seen with the playing around with the CS bits of the TCCR, we can set these. So the size of the time delay depends on the clock crystal frequency and the timer's register. So prescalers can be used to increase the delay by reducing the period over there, and it allows to divide instruction clock by a factor of 8, 64, 256 and 124. So by using this approach, we can easily find out the prescale values or the periods that is generally necessary for any type of applications. So I'm just gonna solve an example over here. So find the timer, clock frequency, and its period. For various AVR based systems with the following crystal frequencies. So assume that we have a prescaler one to 64 is used. So that means we have got the crystal oscillator, then we have got the prescaler, and we have got to fill in TCNT and values. So the first one is 8 megahertz. So for the 8 megahertz, we just need to do 1 over 64 by 8 megahertz, which is equals to 125 kilohertz. And in this case, T is equals 1 over 125 kilohertz. We have got 8 microseconds. Then we can repeat the same thing for 16 megahertz. So 1 over 64 by 16 megahertz, and that is going to be 250 kilohertz, as you can see, and T is going to be 1 over 250, which is going to be 4 microseconds. And also we can do the same thing for 10 megahertz. So 1 over 64 by 10 mega, that will give us 156.2 kilohertz, and 1 over T, it's going to give us 6.4, 1 over F, sorry, microseconds. So we can use this prescaling values and we can calculate the desired values which is required for the operation. And there's another good example over here which is related with the prescaling. It says, assuming the crystal frequency 8 megahertz, write a program to generate a square wave of 125 hertz frequency on pin port P3. Use timer 0, normal mode, with prescaler 256. Now, in this case, let's open a new page. First, let's do the calculations. what it's saying us is the t is going to be 1 over 125 hertz, which is going to give us, oops, I have to go back. So 1 over 125 hertz will give us the period of the square wave, so that will be 8 milliseconds. So that means when you create this wave, we have 8 milliseconds low, and we have got 8 milliseconds high. Oh, sorry. If the period is 8 milliseconds, sorry, that should be 4 milliseconds low and 4 milliseconds high. Okay? And this means we have got 4 milliseconds as the pulse of the wave, and we know that we have got 8 megahertz clock, so the period of that clock is 1 over 8m, which will give us 0.125 microseconds. So we know the pulse is 4 milliseconds, and we know the period is 0.125 microseconds. So we can say that 4 over 0.125 milliseconds microseconds, and that will be divided with the prescaler, which is 256, which is asked to us, and that means that is going to be equals to 125. You can calculate this. Now, going back to the equation that we have for TCNT, 256 minus 125 will give us 131 in decimal. So in hex, this is equals to 0 hex A3. That means this is our going to be TCNT0 value. So what we have done, we found the pulse, which is 4 milliseconds based on the given frequency of the wave. Then we use the clock frequency and find the clock period. Then we divided those. And then we divided by 256, and we got 125. And if we subtract that 125 from 256, we have got the count as 131 in the decimal and hex 83 as a hex value, and we have to load this with the into the TCNT. So the next thing that we can do, we can write a code for it. So let's write a code for it. Now there are a couple of things that we can do. Up until now, we have seen that we can create these in one main program and use it. But now let's try something else, and let's create this delay as a separate subroutine. So to do that, at the beginning, we have to initialize a stack. So to initialize a stack, or we can write a macro for it so that we can use it whenever we want. So macro init stack LDI LDI R20 high Ramend out SPH R20, then LDI R20 low Ramend, then out SPL R20, and then we can end the macro. So we create a macro for the stack, and then I can use this whenever I want. And let's say init stack LDI R16. So we are going to use port B pin 3 again, so it's going to be 0 hex 08, and then SPI DDRB 3, so PB3 as an output, then LDI R17 0, and out port B R17. So we set the port B equals R17. Then what we can do, we can call the function, let's say delay, or the subroutine, which we are going to initialize the timer and do most of the stuff over there. And when we get out from that subroutine, we have to toggle the pin. So R17 is going to be R16, and our jump begins. So we have to go back and start again, and we can do that over here. So that will begin. Then now we can get into our subroutine, which is delay LDI R20. So the TCNT value is 0 hex 83, and that has to be loaded into TCNT0 R20. Then for TCCR, it's gonna be a normal mode, but with a prescaler set. So we can check from the datasheet and set this out. It has to be 0 hex 04, and out TCCR0, which will be R20 in this case. So timer 0, normal mode, prescale 256. And as we have set that one, now we can check for the interrupt flag in R20, IFR. So we can read TIFR, then SBRS R20 TOV0 overflow flag. So if TOV0 is set, skip next instruction, and our jump, let's say again. So again has to check until we have got it set, so we can check the interrupt flag. And once that is done, what we can do, we can clear and stop the timer. So 0 hex 00 out TCCR0 to be R20. So stop timer 0, LDI R20, and that will be, we are setting TOVZ0 to be cleared, and that will be out TIFR R20. So clear TOV0 flag, and then we have to return back to the main function, and we can go back. So I think that's it. So we have used the prescaler, so that's why we have set TCCR0 with the prescaling value, and we have calculated TCN to be hex 83 based on the prescaling value as well. And that's the solution for this part. And the next thing that we need to consider in this chapter is going to be timer 1, which is a 16-bit timer, which we are going to cover next.